So in this section today, what we're going to do is, this is section 3.1. What we're going to look at is graphing quadratic functions. Okay, that's what we're going to see today. And this is just a reminder. I think I've mentioned it before, but a quadratic function, okay, this is a function of this form. So it's a function that can be written this way. Written meaning you can, do those algebra processes, like add the same thing to both sides, multiply both sides by the same non-zero number. So it's equivalent, I guess, to this side, in other words. And of course, A, B, and C, those are numbers. A is not 0. If A was 0, then we would just have bx plus c, which we know already is a line. So we have this. So basically, the right-hand side is a polynomial of degree 2. Okay. The graph, remember, it looks like the graph of y equals x squared. In the graph, we call it a parabola. No matter what a, b, and c are, the graph is called a parabola. What's nice about these functions is that their domains are all the same. Remember, for a domain, that's all the inputs. That's all the numbers you could put into X and get an output that makes sense. So in this case, the domain would be all real numbers, and that's what this notation is saying. This is notation for all real numbers. The range will vary, though. The range basically is going to be from some number either up to infinity or down to minus infinity. You'll see it's actually going to be a half open interval, the range, and it will depend on A, on B, and on C. Now, here I just, produced some examples using, using GeoGebra. And this is the graph of y equals x squared plus 1. As you can see, it looks almost like how do I say this? Like a U, I guess, but without that little tail, if that makes sense. That's what the graph looks like. We have seen y equals x squared before. And here we're basically just shifting the graph upward 1 unit, upward, vertically. Okay. But here, hopefully, you might be able to see that let me get back. I'll come back later to the range. Well, I'll say it now. The range is actually from 1 down here, but it keeps on going up to plus infinity. I mean, you can hopefully see that because if you were to think about what we did in section 2.4 with functions, remember how we got the range? We took the graph and drew these horizontal lines, right? To the y-axis. I mean, we did it there for line segments, but that process does work for any function for any time you have y as a function of x. But if you were to keep doing this, you hopefully can see that any number above, including 1, is going to be in range. So the range would be everything from 1 to infinity. Here, okay, the big difference really is that we're taking this graph and flipping it. That is, we're turning it upside down. Hopefully that makes sense. And we're going to get this graph opening down. And in this case, the range is from 1, but it's going to go down to minus infinity. Again, same idea. You have these horizontal lines here. These horizontal lines, right? If you draw them, you would see that every number on the y-axis from 1 down would be in the range. So it's almost like we're taking the graph and projecting it onto the y-axis. So here, let me go back to this one. For this one, we would end up with, oh boy, all this. Oh boy. And here, we would get all this. I know my drawing skills aren't the best. Bear with me. Basically, here, you would get everything from 1 down to from minus infinity to 1. Here, from 1 to infinity. So you get half-open intervals for the range. Notice here, A is 1, right? A, remember, is the leading coefficient. When it's not written, it's understood to be 1, so it's positive. This is opening upward. Whereas here, A is negative 1, and the graph is opening downward. Well, that's no accident here or coincidence. That's going to happen always. Whenever A is positive, the graph is going to open upward, kind of like what we saw before. So let me just draw this. It's going to look something like this when A is positive. When A is negative, it's going to be down like this. It keeps on going, the graph. Keeps on going up or down forever and ever. So we have that now. Okay, now, going back to the graphs on the previous slide here, let me erase this. Let's see, hopefully they saw it. Here, notice on both of these graphs, okay, there is a point where the graph turns around. You know, if you're coming down on the graph, if you imagine yourself walking along the path, right? There's a point here. Here, it's this point where the graph turns around and you walk back the other way, in the other direction. Here, the idea is you're walking along the graph, right? And you get to the top, so to say, and then you turn around. It's almost like here we have the top and here we have the very bottom. These points are called the vertex of the parabola. Okay, that's what these are called. So there's a point on the graph where the graph turns around. Or if you look at these drawings, where you reach your lowest for A positive, where you reach your highest for A negative. That's called the vertex of the parabola. What's nice about graphing these quadratic functions is it's really not that terrible. It's almost procedural. You find out what A is, you get the vertex, you get some other stuff, and then you just sketch the graph. Really a lot easier than other functions. So we have the vertex. We know what happens with A. We have that. Now, if you were to look at this graph, which is actually x squared plus 1, y equals x squared plus 1, hopefully you can see this, but you can imagine taking the graph, both sides, folding it along the y-axis. And if you were to do that, both halves would line up exactly. You know, they would fold over each other. In other words, you could think of the y-axis as like a mirror, and the graph, and on the left side, that's the mirror reflection of the right side. They're mirror reflections of each other. Or in other words, they're symmetric about the y-axis. What I'm trying to say is there's a vertical line through the vertex. In this case, it happens to be the y-axis. That's called the axis of symmetry, and the graph looks exactly the same on each side of the line. Maybe not exactly the same, but it looks similar. You know, again, you can imagine folding the graph about the y-axis, about the axis of symmetry. Both halves would line up. Hopefully that made sense what I said. I really hope it did. I mean, it's written here anyway, so it takes a little bit of visualization. So we have that as well. I mean, that's easy to get anyway. It's just a vertical line through the vertex. So it's always going to be of the form x equals something, as we'll see. And really from there, we have all the y and x intercepts as well. But we know how to get those intercepts. That's really all we need to graph a parabola, to graph a quadratic function, Because they're going to look similar to this. or to negative x squared plus 1, which is when, as we saw already, the graph is turned upside down. Okay, so we have that so far. Now, here's before we get to actual examples, here's another form of a quadratic function. It's actually pretty useful. I mean, we're not going to focus on it too much, but it's still, it's very useful to know. Yeah, let me keep those. Let me just quickly, this should be function, not equation, but hopefully you can see from here. Okay. Excuse me, we have this form here. I mean, this is useful, don't get me wrong, and if you know about vertically and horizontally shifting a graph, I didn't go over that, but if you know that, you can actually use this to graph the function. The a in front is still the same a, it's the leading coefficient. So if this a is positive, it opens upward. If it's negative, it opens downward. HK actually turned out to be the vertex of the parabola. This is, again, called the standard form of the quadratic function. I had equation here, should have been function, sorry about that. HK is what we call the vertex of the parabola. Again, that's the point where the graph turns around, or it reaches its max or minimum, as we saw already. So if you have this form, you can easily get the vertex. You just read it off, basically. If you have the other form that we had in the definition, you have to do a little more work, not much more, it turns out, to get the vertex. Actually, by what I'm going to show you, it's not much more work. And both of those forms, okay, both of those forms, are for the quadratic function. I'm not sure what the other form actually is called, if it's called anything, but this is called the standard form. But you can go from one form to another. To go from what we have, actually it's on this slide, to go from what we had in the definition here, I'll get to this stuff in a minute. To go from here to the standard form, you have to use a method called completing the square. I'm not going over that for time consideration. It is in the textbook if you want to read about it. There's also plenty of websites out there that can help you with it. I mean, it's not an easy process, but you can convert from here to here. But as you can see on the slide, we actually don't have to. To go the other way, you just FOIL, like we've seen earlier. Let me